Now, when we computed the homography matrix given two images, we essentially took all the pairs of matching features and used them to compute the homography. But we know that not all these pairs necessarily correspond to valid matches. For instance, you may have 2 points in these two images that have exactly the same local appearance, the same blob, so to speak, in the context of the SIFT detector. So you get a match, a perfect match, because they have the same appearances, but it just happens that they don't come from the same point in 3D. And so this would not be a valid match. So unfortunately for us, there is no way of telling the difference between a valid match and an invalid match before you compute the homography. So we have to deal with this issue of there being inliers, which are valid, and outliers that are invalid. And that's done using an algorithm, a very clever technique called RANSAC. So let's come back to stitching for a minute. You have image 1, image 2, and you have all of these, let's say, perfectly valid matches. All good. If you use these to compute the homography, we are in good shape. Unfortunately, you're going to get these other matches, which are bad matches, invalid matches. It so turns out that the appearance at this point is a perfect match with the appearance at this point, but they do not correspond to the same point in 3D. They are not projections of the same point in 3D. So we have outliers in this set of matching pairs of points, and the question is, how do you compute a homography that's valid in the presence of these outliers? So that brings us to this technique called RANSAC. RANSAC was also developed in the early 1980s or so in computer vision, but has broad implications. It can be used to solve many different problems where you have an outlier problem. So in particular, you can have a large number of outliers and RANSAC still works pretty well, as long as the number of outliers is less, say around less than 50% of the total amount of data that you have. But that's a big number. That's a lot of outliers. So let's see how RANSAC works. And we'll use the problem of computing homography sort of as an example as we go along. But this is a general algorithm. You're given some data, points, and you're given a model. You have to have a model that you're trying to fit to this data. The data points include inliers and outliers. And let's assume that to fit this particular model, you need a minimum of S data points. In the case of the homography, we know that S is equal to 4. So we're going to use the minimum. So what you're going to do is randomly choose S samples from your data. The minimum number, but randomly chosen. And then you're going to use those as samples to fit the model. So in the case of homography, we randomly go in and take 4 pairs of matching points, and then we fit the model, the homography model, we compute H. Okay, so now you have a model, and then you're going to count the number of points in your data, all of your data, number of points M, that fit the model. What does that mean? You take each point and you plug it into the model, and you see what comes out of it, whether it's close enough, whether that point actually, if you're talking about a pair of matching points, you plug in the coordinates in one image, you get the coordinates using the model in the other image, and you're going to see the distance between what the model gave you and what the actual coordinates are. And that distance you're going to use to determine whether it's an inlier or an outlier. So you're going to basically count the number of data points, in our case, pairs of matching points, that fit the model within some threshold, epsilon. You have to decide what this epsilon is. And then you're going to repeat these 3 steps n times. You're basically going to do exactly the same thing n times because you're randomly choosing. And then finally, you choose the model, in our case a homography, that has the largest number of M or inliers. And that's it. Now you can do one more step after this, which can be added to the algorithm, which is once you've found these inliers, you can go back and recompute your model, in our case a homography, using all the inliers so that it is a more refined model than the one that you computed using just these minimum number of random samples. That's RANSAC, extremely useful. And in order to show you how it works, I'd like to use the case of line fitting. Okay, just as a visual sort of demonstration of why this works in the first place. So in the case of line fitting, let's say you're given this set of points here. When you look at this, you can see that this is the line that you're after right here. You see there's a dominant line right here. That's the line we're looking for. But if you simply take all of these points and you fit a line to it using a pseudo-inverse technique, if you remember the least squares method that we discussed earlier in the lecture on boundary detection, if you just applied that technique using all of these points, it's an overdetermined system, you just use the pseudo-inverse, you're going to get this line right here. And this line essentially has only 2 points in the whole set that lie on it, 2 inliers right here. Clearly not the line that you're looking for. Whereas now let's take a look at what RANSAC does. So remember that to fit a line, you need a minimum of 2 points. So we're going to go in and randomly choose 2 points from the entire set. And let's say we chose this point and this point right here. Here's the line that passes through those 2 points. And you find that there are 2 more points that lie close to it. So you have 4 inliers in this case. Go back and do the same thing. This case, you have these 2 points that were chosen randomly, and there's only 1 other point that comes in and falls on that line, so you have 3 inliers. And you keep repeating this. Sooner or later, you're going to hit 2 points that lie on this cluster. That's the key observation here. And that's what happens, and when that happens, you get something like 20 inliers here. And you keep going. Maybe you do this 1,000 times, but you pick the one that gave you the maximum number of inliers, the model that gave you the maximum number of inliers. And like I mentioned earlier, once you've hit that maximum and you found the model that gave you the maximum, you can go back and take all the inliers and then recompute the straight line right here using the pseudo-inverse method, for instance, the overdetermined least squares.